Hey guys, welcome back. It's Mrs. Webb here. Excuse me. We're going to spend a little bit of time today talking about Newton's second law with respect to objects that are moving at an accelerated rate on an incline. And so there's a lot of really interesting questions that can arise when we talk about inclines. The big thing to note when we talk about inclines is that we're going to redefine our axes ever so slightly. So we've always placed our rosetta in a two-dimensional problem, much like a normal X and Y axis would be, right? But in terms of a ramp, since a ramp is angled a certain amount to that horizontal, what we do in order to simplify our lives for problem solving is we rotate the rosetta. And we rotate it so that the quote unquote X axis or the parallel axis is in line with the surface of the ramp, right? So this ramp surface becomes our new axis, our new parallel axis, and then the perpendicular to the surface of the ramp becomes our new perpendicular axis or a y-axis. And then everything else is much the same in terms of our solutions, but wrapping your heads around that particular concept takes a little getting used to. The other thing you need to note, and you guys already know this, is that because gravity acts straight down, that means that, and this should actually not read X, so let's just cross that out. Oh, let's do it in black. So what that means is that now gravity, in terms of this new rotated rosetta, now gravity is going to be acting at an angle to our parallel and at an angle to our perpendicular, right? So it's still acting straight down. It's just that because we've rotated our rosetta, now the gravity isn't sitting on top of the y-axis like it has in all of our other problems where things have been sliding on a horizontal surface. Now, as a result of this rotation of the x and y-axis, the force gravity is sitting at an angle to the x and the y-axis, or the perpendicular and the parallel axes. And the thing to note is that when that happens, the angle that's formed here between the y-axis and force gravity is equal to the angle of the incline. So keep that in your memory because that is an important thing for you guys to remember so that you're able to solve these problems. And I've given you the note here and highlighted it for you. Now, in these notes, I'm referring to this as force gravity X, but truthfully, you should refer to it as force gravity parallel to the surface, which is how we've been doing it in class this semester. So it shouldn't be anything new for you guys. Now, when something slides downhill, what happens, because a lot of times you guys know that you don't actually have to be pushing on anything in order to get it to slide downhill. A lot of times it'll just start moving by itself in that downward direction. And it doesn't mean it's just spontaneously moving. What's happening is because this force gravity is at an angle to our perpendicular axis, and now that means we're going to have a parallel component to the force gravity. What actually gets that object to slide downhill is that parallel component to the force gravity. That's really what's making something move downhill or slide downhill. And that's the other thing to keep in note, is that it is that force gravity, and I'm just going to change that X to be a parallel. It is that force gravity parallel that is the force that's going to cause an object to accelerate downhill. Okay. So think about this. If we were to increase our force gravity, because you guys know if we had something at a very low incline, more than likely the object that's sitting there, it's not going to go anywhere. But if we raise the incline, all of a sudden that object starts to move. And the question is, well, why does that happen? Well, what happens is, in this situation, if we look at our force gravity, we draw our perpendicular component, we draw our parallel component. You'll notice that this parallel component of the gravity is really quite small in magnitude. Now, if we increase the angle to something that's quite steep like this, we're going to get that the force gravity parallel is going to get much, 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 much larger. And as a result of becoming much, 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 much larger, that's going to cause the object to accelerate down toward the base of the hill. Okay, so what causes an object to slide as the incline gets steeper and steeper and steeper is the fact that as the incline gets steeper and steeper and steeper, that force gravity parallel gets longer and longer and longer in magnitude, until eventually, if we have an object where, let's say it's a vertical wall, like you're climbing up a vertical wall, right? If something's vertical like this, well, the force gravity that's parallel to the surface is equal to the force gravity itself, right? So eventually that force gravity parallel will just match the magnitude of force gravity, right? And the y component, or the perpendicular component, will just go to 0. So that's essentially why something will begin to slide if you increase the steepness of the slope. So that's kind of the ins and outs of ramps. Now that's you know, it seems fairly simplistic, but it's a fairly intense kind of concept to wrap your brains around, and it's something that gives students a little bit of trouble. So give yourself a little time to get used to that. But I've got some examples here for you. And we've got a 50 kilogram box is sitting on a 20-degree incline. Force friction is 50 newtons, and we want to find what's the acceleration. So here's our 20-degree block. We're going to draw our free body diagram. Now, I've drawn my free body diagrams on the block, but remember, always draw them separate. We've got our force gravity pulling straight down. There's a force friction. Now, it hasn't told me the force friction is up, but intuitively, we should just know that, because if we're on a ramp, things are always going to slide down the ramp. And so friction always opposes that direction of motion, which means that the friction will point up the ramp. And then our force normal will always point perpendicular to the surface, right? So that's our free body diagram. Now, my preference is always, and actually I said I hadn't drawn it separate, but I have. So here's my free body diagram here. The thing for you to note is that if this angle is 20 degrees, that means that this angle right here between my y-axis and my gravity is going to also be 20 degrees. And because that force gravity is at an angle to the y-axis, that means that we're going to have a y component and an x component to my force gravity. So this will be the one that runs along the perpendicular will be the force, or the one that runs along the y-axis will be the force gravity perpendicular. And then the one that runs parallel to the x-axis will be the force gravity parallel. So my preference is always for you guys to draw this diagram. This is not officially the free body diagram, but I prefer you guys draw this diagram, because if you do this, now you know when you set up your sum of the forces equation, you know specifically what it is you're needing to sum together, which vectors. So in the y direction, there's nothing happening in that perpendicular direction. So I just make a statement saying F net is equal to the sum of the forces. Oh, what did I just do? And that F net is equal to 0. So we can just forget about it there. Specifically, what I'm interested in is the force net in the parallel direction. So let's put in that parallel. And this one's perpendicular. And the force net parallel is going to be the sum of the forces in this perpendicular direction, or parallel direction, which is parallel to the x-axis, or the surface that the object's sliding on. Now we know the object is going to accelerate, so that means that we're going to have a mass times acceleration, and the sum of my forces is my force gravity parallel plus my force gravity friction. I don't know specifically what this force gravity parallel is, but I do know the mass of the object. I know gravity, and I know that because force gravity parallel is opposite the angle, remember SOHCAHTOA, sine is opposite over the hypotenuse. So 50 times 9.81 times sine 20 will give me the magnitude of this force gravity parallel, plus my force friction, which is negative 50 newtons. Negative because I said downhill was positive. And if I solve for this, I get positive 2.4 meters per second squared, which means 2.4 meters per second downhill. So that's a typical problem. It's very much like what you've been practicing already. The only difference being that we're now on an inclined surface, and so we've tilted the Rosetta, and we've got to take into account the big factor that gravity is now at an angle to our y-axis. So I've got another example here for you guys. So we've got a mover pushes a 50 kilogram box up a ramp at a constant rate. And remember that constant rate is your code word for uniform motion or acceleration equal to 0. And they've told us that the force of friction is 30 newtons. What's the force applied? Now this mover is pushing the box up the ramp. So if the motion is in the upward direction, that means that friction is going to be down. So again, here's my free body diagram. My free body diagram, I'm showing force gravity is acting down, force applied is acting up the ramp, force friction is acting down, and force normal is perpendicular to the surface. Now, we know that because we're at an angle, we're going to have this 30-degree angle to our y-axis, our brand new y-axis. So that means that force gravity is going to have a y component and an x component, which we call the perpendicular and the parallel component to the surface. So I'm going to redraw this diagram just so that I can get straight in my mind what it is I have to sum together. So if I redraw this, I'll see that my perpendicular component is right here. So I've put it in here. My parallel component is here pointing down the hill. So it's pointing in the same direction as force friction. So here's all the forces I'm working with. In the y direction or in the perpendicular direction, there's not much happening. The box isn't going to move up or into the ramp, up off the ramp or into the ramp. So I can just focus on the parallel direction. They told me that I'm working, or this mover is working at a uniform rate, which means acceleration is equal to 0. So F net is equal to the sum of the forces in this parallel direction. I know that F net is equal to 0. And in this parallel direction, I've got force applied plus force gravity parallel plus force friction. So that's my sum of the forces here. If I insert my values, I know that I've got 0 newtons plus force applied minus 245.25 newtons. I've calculated that over here on the side for you so that you can see how I arrived at that. But that's something that typically we're just inserting straight into our sum of the forces equation. And then I know friction is negative 30 newtons. Both of these are negative only because I said downhill is negative. If I rearrange and solve, I get that my force applied is positive 275 newtons or 2.8 times 10 to the 2 newtons uphill. So that's a typical ramp problem. There's a couple of other scenarios that could arise that you'll see. We'll do a couple of examples in class, but we could mix one of these ramp problems with a pulley, for example. So maybe on this end we have a pulley and there's a mass down here that's going to cause this, kind of like the Fletcher's trolley, except now our trolley is on an incline, right? So there's a couple different scenarios that we can do, but that's the premise for it. Everything is the same as you've been doing all along, except that now we are tilting that Rosetta, making gravity behave act at an angle. So as usual, guys, if there's any questions, let me know. We'll do some examples together in class, but bring your questions to class so that we have a starting point when we see each other next. And on D2L, I have some practice for you called ramps. And if you want to get a head start on that, it's there for you, and you can give it a shot before we see each other. So I hope you're doing well. Take care, and we'll chat soon.